We have an assignment due tonight. I have plentiful office hours today and after my second class at noon as well, so feel free to stop by anytime you have availability, and I'll do my best to help you out, especially knowing that today is the due date. Remember that we also have an ongoing project that you have a bit of time left for, but given the looming exam next week, whenever you have time, I would be focusing on that project, especially now that we've gone over CYK. You have done it on the homework that's due tonight, and then you should be good to go to get started. If you want some help with a nudge in the right direction for thinking about setting this up and designing a solution, come talk to me. I'd be happy to help you get started. Last time, we finished talking about NPDAs and getting some experience with designing non-deterministic pushdown automata. And so now we're going to look at an application of Greibach normal form, which is the conversion of context-free grammars into non-deterministic pushdown automata. So, things that we know as we get started. For every context-free language, it makes sense that there's an NPDA that accepts it. It's that visual form that represents that class of language, just like a DFA or NFA did for a regular language. And in order to be able to prove this, we need to be able to show that there exists an algorithm that can convert from one to the other. That proof is significantly simpler if we assume that a grammar is in GNF. So the first thing is that we need to be able to convert an arbitrary CFG into Greibach normal form. Since this isn't something that is a prerequisite in quite the level of CYK, I'm not going to go through that algorithm, but that algorithm absolutely exists. Once we do that, we're going to go through a leftmost derivation of each production. And as we do that, the fact that Greibach normal form has a single terminal followed by 0 or more non-terminals, the single terminal becomes the edge label. And the non-terminals define stuff that is to come. If we were to expand the leftmost non-terminal of that, we would get as its first character another terminal. So that really just describes the set of states that we need to go through in order to be able to accept strings in this grammar. So let's go through an example. Let's start with coming up with an NPDA for this grammar. So we first need to convert it into GNF. How could we do this? What is an equivalent GNF to this? How would we go about doing that? Yeah.
Should we introduce a non-terminal B goes to B or something?
Yeah, so the only part of this that is not in GNF, no, this isn't a simple grammar, so it's okay to have these two A's here. We just need something that is a non-terminal here that represents this. So we're going to recreate this S as A. We're going to keep the capital S, but then we need something, some other non-terminal that represents the rest of that string, or A. This A was going to be that BB. So we can say B, but now we need something that represents that B, that last B, and we don't have that. So we need to make another non-terminal that goes directly to that B, and only that B. That is that A. That'll look better. So that's in GNF. It's not too hard of a conversion once you get the idea of it. Just whenever you see series of terminals and non-terminals like that, just make a new non-terminal that represents it and then dig into the details to find what those terminals should be. So I think this is exactly what I have here to be revealed momentarily. From there, we're going to be starting with the start symbol. So we need the ability to push non-terminals onto the stack. And that's going to become our stack alphabet. And the way that we've been using binary before, the new stack alphabet are going to be the language, the symbols that are the non-terminals in our grammar. So the first transition for this is a transition that pushes the start non-terminal onto the stack. This is what needs to be evaluated. S arrow something is going to expand into a string that is in this language. So starting with that S on the stack, we're going to be popping and pushing. We're going to pop a left-hand side and push a right-hand side and continue to do this. And whenever we have a terminal on top, we'll read the terminal from the input. Whenever we have a non-terminal on top, we will have to pick one of the derivations, one of the productions that adhere to that, and put that back on the stack. So here is the production for putting the S on the stack. We have that same Z bottom of stack character. It's not the S. We still need the Z that says the stack is empty. Once you get rid of that S and everything that we turn that S into, then we know that we have resolved it. We've turned it into one of those strings in a language. Then we're going to look at every production defined by the current non-terminal and make a rule for each of them. So when we have the left-hand side arrow, right-hand side, S arrow, A capital S capital A, we read the A from the input. So the transition label for this is reading an A, popping the S, the left-hand side from the stack, and pushing the right-hand side of every non-terminal that appears after that lowercase a onto the stack. So if we're drawing an NPDA for this so far, we have an initial state that is boring. From here, we're going to read nothing, pop nothing, push an S. From Q1 now, we have a transition where we can go from S, let's do this down here, that says that we're going to read an A, we're going to pop the left-hand side an S, and we're going to push the right-hand side, this A followed by this S. Again, we push from right to left. What's on top of the stack after this is the S, because it has to be evaluated first. So that is a legal thing that we could do. Then we have the other rule. Now, this continues on the next slide. I'm just going to continue this process here because I know I have room for it. We're going to read an A, pop the S, push nothing. And that's what this second rule defines. Read an A, pop the left-hand side, push every non-terminal after on the right-hand side, which is nothing. Then we need to continue. We have two more to evaluate here. From this Q1, we could read a B in the string. We could pop an A off the stack, and we could push a B onto the stack in its place. Or we could read a B, pop the capital B, and push nothing. And that defines all of the rules that are possible within this grammar. Once we have just the bottom of stack character, that should be SC, sorry. And this should also, I'm assuming that the bottom of stack character is on there. So you pop the bottom of stack and push it back on. Once we reach that point, then we can read nothing, pop the Z, put the Z back on at the bottom of stack, and go to a final state Q2. So this is the NPDA that represents this context-free grammar. And that's in general the process you would go through in order to convert from a context-free grammar to an NPDA. It's embedded directly within the rules of the grammar, which is awesome. So because we've come up with an algorithm that does this for any context-free grammar, we just convert it into GNF, prove that we can do that. Then any grammar in GNF has a simple algorithm that looks at every GNF production and transition, pop, push, and just go through every production and draw the associated NPDA. Any questions on that logic? Seems like the answer is no. Right. Rest of this we already talked about.
I do just want to ask,
Yeah,
we're basically looking at the non-terminals in NGA for that one, like, that's all we care about.
we do care about the,
I mean,
oh,
like,
it like is the stack characters.
like the left-hand side of all of the production rules, that's the only thing
Yeah.
we're counting.
That's what we're popping as we do this. That's what we expect to be on the stack to be able to do that rule.
But we're never pushing any like terminal characters.
Correct.
Okay,
Yeah, the terminals are always the edges and the non-terminals are always the stack characters,
okay,
which is really cool. It's a way to distinguish between kind of the input alphabet and the stack alphabet. One is the terminals, one is the non-terminals. And it's like the primitives and objects in a language. The states then represent the ideas, and the transitions between them are the characters that we read. Yeah.
I don't quite get with the, so you have like edge of Q1, B equals, and then like the second
Yeah.
parentheses Q1 lambda. What is the Q1?
So this is the from state. This is the character that we read. This is what we pop from the stack. This is the state that we get to, and then this is what we push. So it's the exact same information of what appears on the edge. It's just now defined as a transition edge transition instead of something visual. Good questions? Anything else? Yeah, so the reason this becomes a bit cluttered as we start looking at these is that we end up with a state that has all of the transitions associated with it, with that grammar. So we had Q1 and we had 4 transitions for that for a grammar that had 4 productions. If we had a grammar with 100 productions, then we would have a Q1 with 100 self edges. And that it very quickly scales into something that's difficult to visualize. So because of that, it's very useful to group the like transitions and write them as a series of written transitions instead of something that is a state machine. It's nice to be able to visualize it, but it's not always possible, especially for larger grammars. Let's have you get started with one, and we'll probably have to wrap this up tomorrow. But let's look at a grammar here. Already in GNF. Answered my own question. So go ahead and draw an NPDA that accepts it. The first question I'll have for you as you're designing this is how many states will it have?
3.
3. Yep. So go ahead and spend the last few minutes of class polishing this off.
Are there 3 self edges? For this one?
There should be as many as there are projections on grammar.
So 4.
There should be 1, 2, 3, 4, 5, 6.
I see. Okay.
6 self edges from Q1 to Q1. You need to push the start non-terminal on, going from Q0 to Q1. 6 self edges in Q1 representing each production in the grammar, and then the final edge to a final state on the bottom of stack character. We are out of time. Try to finish this off between today and tomorrow, and we'll come get an answer at the start of class tomorrow. Reminder that I either need exams back or I'd like to talk to you about any concerns you have over grading. I'll handle that right now and then be up in my office momentarily.
Well, that's good.
Oh.